Hey, here's another screencast on an optimization example that I'm calling plankton. Here's the problem statement. So we've got a phytoplankton, and they use photosynthesis to create energy. That means they take light and they convert it into the kind of energy that they need to survive and reproduce. So we're going to try to understand that. Here's the problem. The rate in milligrams of carbon per cubic meter per hour at which photosynthesis takes place in a phytoplankton is modeled by the function P equals 100 times I over I squared plus I plus 4, where I is the light intensity, measured in thousands of foot candles. For what light intensity is P a maximum? This is the problem statement. It's pretty involved, lots of words, lots of units. You read it and it's easy to get lost, but remember, you're always asking the question, what is this question asking me to do? And usually the question's at the end, right? And it's stated as a question. For what light intensity, that's I, is P a maximum? Oh, so we're looking for a maximum. The problem lays it out there. We're maximizing this function P. We know from calculus that maxima occur at critical points, so let's look for critical points. Critical points come in 3 flavors: endpoints, singular points, and stationary points. Let's look at endpoints. These are endpoints of our independent variable. Our independent variable in this case is light intensity. This photosynthesis function, it's a rational function. We know rational functions are continuous everywhere they're defined. If we look at this, we'll see in a second that this is defined for all real numbers. So the tendency of a student would be to say, well, we don't have any endpoints because I could be anything. But remember, this is the real world. And so I is an intensity. It's a measurement. And it doesn't make sense to have a negative intensity. So our I could be as small as 0, but it could be as big as we want. So with this observation, this tells us that we only get one endpoint, I equals 0, from the context of the problem. Yes, this function, it's defined everywhere, but in our problem, I has a specific meaning that dictates that it has an endpoint here. So that's the first critical point. For these other critical points, the singular point and the stationary point, we'll take a look at those together after we compute the derivative. Let's do that now. So P prime, we need to use the quotient rule. So that's the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. Let's simplify this before we do anything else. In my numerator, I've got 100. That's a common factor. I could pull that out. And if I distribute this I through the 2i plus 1, we'll see we can write the numerator as 100 times I squared plus I plus 4 minus 2i squared minus I. And let's do one more simplifying step before we start asking questions about the function. Upstairs we'll see these i's cancel. That cancels with that. And we're left with 4 minus I squared. Because we've got 1i squared here, negative 2i squared's there. It leaves us with a minus I squared. So there's our derivative, p prime. We're interested in singular points and stationary points. So let's look at singular points. We'll do this algebraically, and then I'll return you to a principle I want you to remember that would allow you to answer the question immediately if you remembered that principle. But let's just look at this algebraically. Here's our expression for the derivative. Singular points are places where the derivative doesn't exist. So in this case, it would be where we get division by 0. So singular points are going to occur where I squared plus I plus 4 is 0. I'm trying to think of a way to do this, how to factor it by I, but I'm not. So let's use the quadratic formula. The quadratic formula says roots of this equation have the form I equals negative 1 plus or minus the square root of 1 squared minus 4 times 1 times 4. Oh, I see. Then all over 2a. But what you see here, this is a negative number. And so solutions to this equation here are imaginary. That means I never get division by 0 for a real number. So I don't have any singular points. Okay, now let me remind you of a fact you already knew. This should come as no surprise. This was algebraic result here. Our function p is a rational function. What do we know about rational functions? They're continuous everywhere they're defined, and they're differentiable everywhere they're defined. So everywhere that this denominator doesn't equal 0, my function's nice and differentiable. This denominator and this denominator are about the same. This denominator vanishes exactly where this denominator vanishes. So if this were to vanish, then this were to vanish here. And so the place where this vanishes are not in the domain of my function. So I never expect to have singular points for rational functions. That's the way we summarize it. Okay, let's now turn to stationary points. Let me copy this, bring it to the next page. And we want to solve 0 equals our p prime. To solve this, I can multiply both sides by my denominator. That's the process of clearing the denominator, so let's do that. Get rid of that. And I can divide both sides by 100. That's a constant. That doesn't change the equation. And let me see here, we get this equation. And so this equation has solutions I equals plus or minus 4. But we know our intensity can never be negative, so our solution to our stationary points are I equals 4. Okay, we have all the critical points. Now let's go and use the first derivative test. Let me give myself a little more room on the side here. So I'm going to put our endpoints down. It's 0. I'm going to put our stationary point here, and that's the interval on which we'll work. And on the left-hand side, I'm going to put my factors, 4 minus I and 4 plus I, because it's the sign of those factors that will dictate the sign of my derivative, which I'm going to call P prime. Let me go back to the previous page and show you why that's true. So here's our derivative. 100 is always positive. What I'm dividing by is always a positive. So the only thing that changes sign is this. This is the piece that dictates the sign of my derivative. And that's right here. And so it factors this way. That's why I'm just putting these two factors here. So let's use those. The second factor, 4 plus I, it's always positive, because you take a positive number 4 and you add a positive number to it, you get a positive number. That's why these are both positive. The other factor is different. It starts out positive, and then when I gets bigger than 4, it turns negative. These together tell us that the derivative on the first interval is positive, and on the second interval is negative. So the first derivative test tells us that the function P has a maximum at intensity 4. There you go. That's the answer. Thanks for playing.